in chapter 2, we introduce the official big word of calculus, which is the concept of a derivative. We've been working with the ideas around a derivative. Some of you have played with it in a physics class before, but we'll formalize what it means to have a derivative, what the official definition of that is, and then we'll just practice a whole bunch of different derivatives today. So chapter 2, all about derivatives. So yeah, this is our, the two big guys, names that you'll need to know or at least be sort of generally familiar with were Sir Isaac Newton from England, and a man named Gottfried Leibniz, who was a mathematician from Germany. And so these two guys were rivals, competing mathematicians, and they each were developing the derivative independently of each other. And so we'll look at the differences in how they approached derivative, but there are also their similarities and what connected them together. And we'll just talk about all the different ways you can talk about derivative, the different languages that we'll have. So at the end of last chapter, we finished with the idea of a secant slope. A secant slope being a slope that connects two distinctly separate lines from point A to point B. And so point A being here. So that's A comma f of A. So that's the x value and the y value connected to B comma f of B. And then you can find the slope of any two lines by computing their rise over run, their vertical change over their horizontal change. That's the idea of a secant slope. So that was the end of chapter 1. And on the test, I asked you different questions, all with the same question. I asked the same question, but all in different languages. So sometimes on the test, I asked you about the slope of a curve, which was this. I was asking the exact same thing when I asked you about the instantaneous rate of change. So knowing that those two are synonymous, that there's no difference in the process of how you do it, it's just the language of asking is different. And so you should be very, very familiar with the differences in how to ask it and what they actually mean. That the slope of a line is the same as the average rate of change, which is the same as the secant slope, and that is your f of b minus f of a over b minus a. And then the slope of a curve, not the slope of a line, but the slope of a curve, which is the same as the instantaneous rate of change, which is the same as the variation of tangent slope, the main difference is that we throw a limit in front of that. And that's what makes it instantaneous. That's what makes it a single point. And Gottfried Leibniz, the German mathematician, this is what he developed. This was his approach to it. Okay, to think about the idea of a limit. Okay, so that's all background, that's all new, that's all old. The new stuff. We are now going to call this process the derivative. So the things you were learning in chapter 1, finishing up 1.4, we are now going to be calling this the derivative. All right, so in calculus, we define, and this is your big word, the rate at which the value of a function changes with respect to x for any point along a curve to be the slope of the tangent of the curve. So those words, rate, slope, tangent, all of those words together, we call this the derivative. All synonymous, equally interchangeable in questions. The rate of change, the slope of the tangent, the slope along the curve, and the word derivative, all the same. So here is how we write that. The symbol for the derivative is this fraction notation right here. This is the symbology that was also denoted by Leibniz, df over dx. We read that, you can say df over dx, or df dx. A lot of times people just don't even say the word over, they just say df dx. That is the derivative of the function f with respect to the variable of x. So So if I want to change any of the variables, if I have not the x-axis, but say I have time axis, it would be df dt. That would be the derivative of the function f with respect to the variable t, or time. Or if I was working in the z-axis, it would be dz. It's whatever variable you're working on with whatever function. So it could be dg over dx. That means you're working on the g function derivative. All of those things are all just the symbology or the notation of how we write it. That was how Leibniz wrote it. Okay, so what you need to know about Leibniz, he was from Germany. And his main focus was on turning secant slope, which is just plain f of b minus f of a over b minus a, into tangent slope. You learned that in a day. He spent about 20 years working on that, improving it. Okay, so he focused on turning the secant slope formula into the tangent slope formula. And so visually what his would look like is the red line is a secant slope because it connects 2 points. I'm going to draw a green line on here, which is going to have a tangent slope, which means it only hits 1 point, but it's going to have the same angle to it, the same rise over run. So maybe approximately right here. And the slope at that particular moment is called a tangent slope because it only goes through 1 point, but it's running in the same direction as the secant slope. That was Leibniz's big focus. So let's practice that. Use Leibniz's definition to find the derivative if the function is the square root. Now, last chapter, all the functions I gave you were all polynomials, x squared, things like that, parabolas and cubes. This is going to be a square root. How do we do it? All right, so this is what you'll show me. Because you're using Leibniz, you'll start your work like this. df, the derivative of the f function, and the variable is x, so dx equals. And then you tell me the definition that you know to be about this, x approaching a, f of x minus f of a over x minus a. Could it be f of b minus f of a over b minus a? Sure. Whatever variable you like. I like to stick with an x and use an a, but the variable is irrelevant as long as you've got two different variables in the subtraction. All right, and then you show me how this works out. So then this will equal f of x is rad x minus, what's f of a? It's rad a. Okay, so if f of x, if the function is the square root function, then square root x minus square root a over x minus a. And I have showed you this once before. If I plug in x approaching a right now, what would happen is I would get rad a minus rad a over a minus a, which would give me 0 over 0. If I did that, which means if I get 0 over 0, what algebra thing should I be able to do? I should be able to factor, because 0 over 0 is one of the strategies that comes with that indeterminate form. And so I've showed you that this can factor. Will I be focusing my factoring on the numerator or the denominator? Do you remember? Denominator, right. So this is going to be rad x minus rad a in my numerator, and my denominator will factor into rad x minus rad a times rad x plus rad a. It's the difference of squares applied to square roots. So this is reducible. Maybe I write this a little nicer. center it a little bit. Rad x minus rad a. All right, so this is reducible. The entire numerator can be reduced with one of the factors in the denominator. So that doesn't mean my numerator is completely gone. It means my numerator has reduced to 1. And then my denominator is rad x plus rad a. So then we substitute. And once you substitute, you don't need limit anymore. So this will be rad a plus rad a, which is 1 over 2 rad a. And that is called the derivative of the square root function at any point A that you would choose. And what it represents is the angle of the slope at any point A that you choose. On a square root function, the slope will never be the same at any consecutive, every single point will have a different slope because a square root function starts out and curves, and it will never be the same slope more than once. It will always be changing. So no matter what A you pick, if I pick A to be 1, then what slope will I have right there? If I pick A to be 1? 1/2. Okay? If I pick A to be 9, what slope will I have there? 1/6, because I plug in 9 and I square root and I get 3. If I pick A to be 100, then the slope would turn out to be 1 over 20. It will never be the same at any given A point along my function. All right, that's Leibniz, and you've been doing Leibniz for about a week without really knowing it. Okay, any questions on Leibniz? So we got to talk about Newton now. Meanwhile, over in England. Okay, so let's finish this up. Oh, I know it. I want to talk about this too. We use the letter M to stand for slope, just like we did before. Okay, so just like we did before, we'll be using the letter M to stand for slope. We will also be using df dx to stand for slope. All the same, just different ways of writing it. Okay, so if they're asking you for M, asking you for this new way of doing slope. You'll be asked to write a tangent line, which is different than a tangent slope. A tangent line uses the point A comma f of A. So it's the point that you're sitting at, the x-coordinate and the y-coordinate, and it will use the slope df over dx. You will use that point and slope to write an equation in point-slope form. Point-slope form is y minus y1 equals m times x minus x1. This is point-slope form. We did this in chapter 0 when we were working on write the equation of a perpendicular line or write the equation. This was the equation that we used. So we're just changing our notation. So what is y1 right now? What is the y value of the point we're looking at? F of A. The y value of the point is f of A. So we'll take that out and we'll replace that with f of A. What is m now? df over dx. That is what we are using as our slope. And then instead of x1, we are using the x-coordinate, which is this. That is the point-slope form we'll be using. It's still the x-coordinate and the y-coordinate of the point and the slope value. You don't have to distribute that. You don't have to clean it up. You just can drop the numbers in and leave it right there. If you want to distribute and you want to go farther, that's fine. That's your time, but you do not have to. Nobody's going to require that you do that. All right, then normal. The word normal is synonymous to the word perpendicular. Okay, so those are equal. Those two words are the same. The point stays the same. The point is still A and f of A. The point does not change. But do you remember how to find the slope of a perpendicular or normal line? What's the relationship? It's opposite. It's also reciprocal. So the slope would be the opposite sign, so negative, and then it'll be dx over df. It'll be the upside down of whatever your derivative was, or whatever your slope turned out to be. That is the normal line. So in point slope form, it'll be y minus the y coordinate equals the normal slope, and then x minus the x coordinate. So those are called tangent lines and normal lines. You need two things. You need to know what the point is, and then you need to know the slope from using the derivative. Okay, we're going to stick with Leibniz for a little bit more. Use Leibniz's definition to write a tangent line to the curve, and the curve is a parabola, at -1. So anytime you see this, write a tangent line. I want your brain to think, I need two things. I need a point, and I need a slope. The point should be easy to find. The x value of the point we are given to be -1. The y value of the point you'll need to figure out by plugging in -1 into the function. So -1 squared is +1 plus 2 times -1. So we get a y value of -1 also. The slope value is where you need to do some work. So the slope value, you're going to have to find df dx, which means you'll need to do a little limit work. And we'll have x approaching a of f of x minus f of a over x minus a, and we're going to work this out. F of x is x squared plus 2x minus f of a is minus a squared minus 2a. That was a spot that I saw a couple of you on your test miss. You missed the distributing of the negative. I need to subtract all the parts of f of a, which means it's not just minus a squared plus 2a, it's minus a squared and then minus 2a. I have to subtract that. Now we need to, if we plugged in a right now, we would get 0 over 0, which means we must be able to factor this. So let me show you the right way to factor. This actually was one of your homework questions the night before the test, and some of you were asking me about it. So let me show you the best way to factor this. To factor this, you want all the squared things closest to each other. So I would suggest you reorder this so that you have x squared minus a squared near each other. Put those first. And then put the plus 2x and the minus 2a next. There's still nothing we can factor or reduce yet, but we're close. The next step is partially factoring. So we're going to look at this part, that section, say now that I've put those squareds together, those square terms near each other, I can factor those. And that factors into x minus a, x plus a. And then I'm going to look at the back half of the problem and notice that there's something I can factor out of those as well. What can you factor? A 2. So just out of those, I can put a plus, and then I can factor out a 2. This is called split factoring or partial factoring. You only focus on one section of it at a time, grouping 2 together and then group the other 2 together. I still can't reduce yet because I have this addition sign right here, which doesn't allow me to reduce. So again, sometimes people will mistakenly go like this and reduce those two, but you can't do that because of the addition. I also see people will try and reduce these two. You can't do that because of the addition either. What you can do legally with algebra is get yourself common denominators, because an addition problem needs common denominators. So I can put the first group over its own denominator, and I can put the second group over its own denominator, and then with big parentheses surrounding the whole thing, you're allowed to reduce. So then that will give me, now I can reduce the x minus a's, and I can reduce the other x minus a's. So that will give me x plus a plus 2. Then I can plug in the number a to that, which will give me a plus 2, or 2a plus 2. Okay, it's a lot of work to show that. This is the algebraic proof. I know some of you know the shortcut already. This is the algebraic proof. Okay, you need to be able to prove it, not just know the shortcut. But this is not yet the slope, because where do I need to know where the slope is? At what number? -1. At -1. So I'm going to put -1 into this value for a. So this will be 2 times -1 plus 2, which ends up to be 0. So I have a slope of 0. What does a line with a slope of 0 look like? Okay, it looks like a horizontal piece. And because this graph is a parabola, it means I'm sitting at the vertex of the parabola, the bottom edge of the parabola where it has a horizontal piece. All right, but the final part, I need to write my tangent line, and my tangent line has to be in the form that we asked for. So the tangent line would come out as y minus y1 equals m times x minus x1. That's a tangent line. So then replace the y1 with the y value, replace the m with the slope value, and replace the x1 with the x value. So if we replace all of these, we will end up with y plus 1 equals 0 times x plus 1. You do not need to clean that up. You do not need to distribute. You don't need to do anything. You could just leave it like that. You may clean this up if you like, but you don't need to. All right, any questions on that? Yeah.
Just more of, do you want us to put df of dx is equal to the limit every time?
Okay, that's a great question. So Jackson's wondering about this part right here. Do I need to put that? Okay. That is, that notation is distinctly connected to the Leibniz definition of f of x minus f of a. So you're basically announcing this is the form, what I'm going to use. Okay? Newton's definition has different symbols. And so if you're going to use that, then you would be using you would announce it with his notation. So yes, so that you're telling, especially if the directions would tell you which one to use. Sometimes the directions will just say find the derivative, and then you can pick which one you like better.
I'll just do you want us to write it for every time we write limit?
No, just the first time.
Sorry.
Just the first time.
That's good.
Oh no. Does yours? What does yours say? It's supposed to say the two shall become one. I don't know what happened to that. All right. The two shall become one. All right, this has a double meaning. The two mathematicians shall become one in what they were working on, but also the 2 points they're working on shall become one. We're going from 2 points to 1. We're going to, here's how Newton, meanwhile back in England, Newton was working on his same idea. Newton came up with the notation of prime. So this is Newton's notation for the same thing. We read that as prime. We say f prime of x, which is the exact same thing as the derivative of the function x. Whereas Leibniz put his as a fraction like this. Okay, the derivative of the function x using the function f using the variable x. Newton wrote the prime of the function f using the variable x. It's just two different guys working in two different countries, working with two different notations, coming up with the exact same answer every single time. Newton wrote his because Newton primarily was a physicist. He was not really a pure mathematician. He was doing this so that his physics would work. And so he focused all his energies on things that were polynomials. And so go ahead and write down at the bottom here that Newton's really only works well for polynomials. there was this whole drama about Newton suing Leibniz for stealing his work, and they took it to court. But the court was, the judge of the court was Newton himself. Maybe some conflict of interest there. So he declared himself the winner. And so all the books published Newton's method. And so Leibniz's was completely forgotten for almost 200 years. And then people found Leibniz's work, and it came back into prominence. So there's a whole thing. Well, we're going to watch a YouTube video about it. But it's drama of the day. All right. But Newton's was awesome for physics. But there's a lot of other math that doesn't use polynomials. What about sines and cosines? What about logarithms? What about square roots? What about exponentials? Like, that's when people realized Leibniz's was so much better than Newton's. But Newton has become, by history, named the father of calculus because he declared himself the winner in that sham little court drama they had. All right, Newton used, and there should be a subtraction if yours got deleted. So what does it look like Newton is using instead of f of b? He's not using f of x. What is he using? No. Look at the formula. Not h either. What is he using instead of b? X plus h. He's using this instead of b, and here is instead of b. It's like exactly the same. Okay? Leibniz did f of b minus f of a. Newton said, well, instead of b, I'm going to use x plus h, and I'm going to use, so this is how Newton did it. But the idea is that point A and point B are getting so close to each other that there is practically no distance, measurable distance between them. So close to each other. So if A is here and B is coming so close together, and how big is H then? H is the separation between, okay, it can't be exactly 0, but it has to be approaching 0, right? They have to be so close to each other that they are approaching 0. This was just the way Newton wrote it, okay? Yeah.
I'm sorry, I don't know if I'm mathing right, but why is h just written on the denominator? With x plus h and minus.
Yeah, so then you can simplify this and say that the denominator would just be the x's would cancel out, and you'd just have h, right? For sure.
Oh,
Okay, but you wouldn't see that without knowing where it came from.
That's true.
Okay, so that's why this is the proof. All right. So let's use Newton's definition. We'll see if we like that any better. Use Newton's definition to write a tangent line to the function when x is 0. All right, so same thing. It says write a tangent line. So that means first you need to declare what your point is. My point is going to be at 0, and what's the y value of the point? 0. Okay, so 0, 0. The slope, this time we'll be using Newton, which is f prime. And so it'll be f of, instead of b, it's x plus h. Instead of a, it's just x. And then the denominator is x plus h minus x. And h has to be very small. H has to be approaching 0. So let's see how Newton's works out. Maybe you'll like it better. Maybe you'll like Leibniz's better. All right, f of x plus h. That means take x plus h and put it into the equation. So if I put x plus h into the equation, I'm going to get x plus h quantity squared. And then I'm going to get 2 times x plus h quantity distributed. And then I'm going to subtract f of x, which is x squared minus 2x. And the whole thing is going to be over, if I simplify the denominator, the whole thing would just be over h. So Jackson, now we're just going to have h from our denominator, okay? All right, Newton was a physicist. He loved him some algebra. So now you have to FOIL out x plus h quantity squared, which will be x squared plus xh plus xh plus h squared. That's the FOIL, first outside, inside, last. Then the distributing the 2, so 2 x's and 2 h's, and then the minus x squared and the minus 2x at the end. So it's heavy, heavy on the algebra at the beginning, and then you start to see where things are going to simplify. So what do you notice about the numerator? What 2 things does it have in it? Everything? Pretty close. What first? What first can cancel out? Okay, the x squared can cancel out. All right, what else? The 2x can cancel out. Hi. And then, what do all the rest of the terms have in common with each other? They all have an h. So then we can say if I factor, because if you plugged in right now, you'd get 0 over 0. We need to factor. So I'm going to take an h out of every term. So that'll give me an x plus an h left over plus a 2 all over the denominator that's still h. Now that you've factored out the h in the numerator, you can reduce and then you can plug in h to be 0, which is what h is approaching. So then I will have x plus 0 plus 2, which works out to be 2x plus 2. In a proof, yes. Don't worry, we'll get to the shortcut way. All right, but is this a slope yet?
No.
Where do I want to know the slope at? At 0. So because that's my point that I'm working on. So then my slope at 0 would be 2 times 0 plus 2. In other words, my slope is 2. So all of that to answer the question of writing a tangent line. And the tangent line is y minus y1 equals m times x minus x1. And then we just change those values to be 0, 0, and 2. So y minus 0, 2, and 0, and we have our tangent line, which you're welcome to clean up if you want, but you don't have to. So you decide, do you like Newton better or do you like Leibniz better? It's kind of your choice. Newton does always reduce with polynomials. It is not so good for square roots. It is not going to be so good for exponentials and things like that. Okay, Newton, physics, great for polynomials. Leibniz, better for everything else. All right, for the same function at the same point, what would the normal line be? Okay, well, we don't have to recreate all the stuff. We're practically there. Y minus y1. Okay, well, we know what the y1 is. The y1 was 0. It's the same point as the previous problem. And x minus 0, same point, but what's the normal slope? Well, the slope before was 2. So the slope for the normal line is negative 1 over 2. So you don't have to recreate everything. Once you know the slope, the tangent slope, you can do the normal slope. It only takes one line. Okay, here we go. Find the derivative of the following function. Use it to write a tangent line to the curve when x is negative 3. Did I specify which method you have to use?
No.
So your choice. Okay, your choice. Are you more comfortable with Leibniz or do you want to try the Newton way? It's really up to you. I'm just going to do Newton because we have only done one example of a Newton so far. So write a tangent line means I need a point and I need a slope. My point has to go through -3. And when I square -3 and subtract 1, I get 8. So my point has to go through -3, 8. I'm going to do Newton just for practice. So Newton's definition will be f of x plus h minus f of x over x plus h minus x. That's Newton's definition. Instead of b minus a, he did x plus h minus x. So let's work through this. F of x plus h means put x plus h into the equation around the square with a -1. Then subtract f of x, which would be minus x squared, but plus 1, because I'm subtracting the whole function. And then the denominator is the x plus h minus x, which I will simplify. Then we do the algebra. We FOIL, and then we look for what, if anything, can cancel out. So my FOIL will turn out to be x squared plus xh plus xh plus h squared. And then we have -1 minus x squared plus 1. And the whole thing I can simplify to be over h. That's the FOIL. If you FOIL correctly, then you'll see kapow, 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 a whole bunch of things reduce and canceling each other. So canceling first is where x squared cancels out x squared, where -1 cancels out plus 1. That's called canceling because it's addition and subtraction. Then after we factor, we'll be able to reduce. So I factor out, there should be an h in common, and then I can factor x plus h, that's it, x plus h all over h, which reduces, which drives Andrew crazy. He just wants to do it all at the same time. We're getting there. You will.
It's x over h is just x, or xh over h is just x. It just doesn't, no.
All right, and then we can plug in 0 for our h. So we'll get x plus 0, which is 2x. That is called the derivative. The slope then would be to plug in -3 to actually find the slope value. So 2 times -3 is -6. So then I put it all together into the form of a tangent line. So my tangent line will be y minus 8 equals 6 times x plus 3. And again, don't have to distribute, don't have to simplify. Right, I can multiply, thanks. So the derivative is when you get this far. This is called the derivative. The slope value is when you actually plug in the point that you're at, the value of the point, so that you can find the value of the slope. All right, last one. Find a normal line. Before you can find a normal line, you have to find the tangent line. You can't find the normal line without the tangent line. So first you want to set up what the point is. The point is going to be 1, 2. And then we want to find the slope. Because this is not a polynomial, I will recommend Leibniz. So go back to Leibniz, which is f of x minus f of a over x minus a as x approaches a. I would recommend that. The algebra will be much, much easier on you if you go back to Leibniz. So then we have f of x, which is 2 over x, minus f of a, which is 2 over a, all over x minus a. Right now, if I plug in a, I'm going to get 0 over 0, which means I must be able to do some kind of FOIL, factor, common denominator, or reduce. Those are the big things. FOIL, factor, common denominator. Here, it's going to be common denominator. So the common denominator I want to work on is multiplying the first part by a, and the second part by x and x, so that I can get a common denominator. That will give me 2a minus 2x over the common denominator xa, or ax, over the original denominator of x minus a. And I know I've showed you this before, but when you get 3 of those, a top, a middle, and a bottom, I always say make it an even number. Do over 1. That way you can multiply by the reciprocal a little bit more cleanly. So then multiply by the reciprocal, so I will have 2a minus 2x over ax times the reciprocal of 1 over x minus a. And I'm so close. I've done the common denominator. Now I should be able to factor so I can reduce. Do you see what can factor out of there? Okay, there should be a 2 that I can factor out. Yeah, you could take out a negative 2 if you want also. I'll take a positive 2 out just so I can show what will happen. I'll get a minus x over ax times 1 over x minus a. So I ended up with an a minus x and an x minus a. If they were the same, they would reduce to 1. Because they are different, opposites, they reduce to negative 1. So this is reducible, but it reduces to negative 1. So I'll have negative 1 as my numerator and ax as my denominator. Then I'll plug in a times a, or negative 1 over a squared. This is called the derivative. Yeah. Oh, I'm sorry. I missed my 2. This is called the derivative. In order to make it a slope, we plug in the point that we're working on, which is negative 2 over 1 squared, or negative 2. Then I'm ready to write the answer to the question, which is write the normal line. So the normal line would be y minus 2 equals space x minus 1, and I want to put in the normal slope, which is the perpendicular slope, compared to what I got. I got negative 2, which is the tangent slope, so then the normal slope would be positive 1/2. All right, we'll stop there. We'll finish the graphing one later.